Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we are going to stimulate you with some simulations for your statistics students. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough to learn, tough to teach concepts accessible to all my students. I'm excited to be joined by our two panelists, Becky Byer and Tracy Watson. Becky is a nationally board certified teacher who teaches grades 9 through 12. Her current classes at Kelly Walsh High School include AP Statistics, C++, AP Computer Science A, and AP Computer Science Principles. In the past, Becky's taught Algebra 1, Algebra 2, and Visual Basic Programming. Becky has a bachelor's degree in mathematics education from Black Hills State University and a master's in mathematics education from Montana State University. Becky, it's great to have you with us tonight.
Great to be here tonight.
And Tracy has been teaching geometry, AP Statistics, and AP Computer Science at Benton High School in Arkansas for the past 6 years. Previously, she taught college mathematics courses for over 15 years. She's been an AP Statistics reader for 2 years, which she feels was the best PD for teaching AP Statistics. As a T-Cube National Instructor, she enjoys sharing with teachers across the country the appropriate use of technology in the classroom. Tracy, thanks for joining us tonight.
Good evening, Mike. It's great to be here with you and Becky.
We're expecting a large crowd, so your audio is muted. Feel free to send any questions to Becky or Tracy using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues, but if you do, try toggling the audio broadcast icon at the bottom of your WebEx screen. At this point, Becky is going to discuss our agenda.
So tonight we've already done the welcome and introductions. We're going to start out tonight with an activity called Pumpkin Patch, which is going to give us a method to look at different sampling methods. We're going to look at convenient samples, simple random samples, stratified and clustered. Once we've talked about how to collect data, then we're going to move on to sampling distributions and explore mean, median, and standard deviation. Then we'll talk about combining variables and do a similar simulation from the sampling distribution. And then we'll wrap things up with a type 1 and type 2 error simulation that deals with both probability for type 1 and type 2 error and how to calculate power.
Becky, thanks so much. And Tracy is going to discuss our expected outcomes.
Our outcomes from these 4 stimulating simulations that Becky created are going to be that you can explain the difference between various sampling methods. You can calculate the standard deviation for a sampling distribution, know when a sampling distribution is approximately normal, and you can calculate the mean and standard deviation for a sum or difference of 2 random variables, and also calculate power.
Awesome. Thanks so much, Tracy. And while you get set up, sharing your screen, Becky, I'm going to put you on the spot for a minute, and Tracy too, if you want to chime in. Tonight we're talking about simulations, and I just want to know if you guys can give me your short five-second spiel about why you think it's important that people who are teaching statistics use simulations.
I think it's the visualization piece and getting an idea in your head of what's going on, but I also think with simulations you get to see the messiness of statistics and the variability, and so that it's not just, you're not always going to roll a 6 every single time you roll a dice, or when you go do a sampling distribution, it doesn't always give you the exact same level. So I think it's really important for kids to see that variability.
Yeah, and I think their first experiences with probability is so theoretical that seeing the messiness of what it is in real life is extremely important, and to constantly remind them of that. And the stimulating simulations do that.
Hey, you guys created the title. I knew that I was going to trip over my words tonight. Thank you so much. It's all
Me
yours.
too, so it's okay.
So
All
the
right,
first
Becky.
activity that we're going to explore tonight is called the pumpkin patch activity. So typically I do this with my students in the fall. So imagine that it's this nice September, October feel. You've had your garden growing and now we're ready to bring in the harvest. And we kind of want to get an idea of how much time it's going to take us to bring in all of the lovely items that we've grown in our garden. So if Tracy will go ahead and click over to page 1.2. Actually, I guess 1.3 from my pages. So here's our pumpkin patch. If you'll notice, your pumpkin patch has 100 little squares. It's kind of been gridded off for us. We have 10 rows and we have 10 columns. You have a nice road system running off to the left-hand side, and you have some water running along the bottom. So for those of you out there who happen to grow things, do you think that every one of those squares is going to contain approximately the same number of pumpkins? Or do you think that there could be some variability due to some factors? And what do you think those factors are? So if you'll go ahead and type that into the chat window, what do you think? If you're going to grow in that sort of a situation, should your field be uniform? Or what do you think might be some factors?
And we're assuming that you are a green thumb and not like me, that I tend to not do so well. I just throw seeds in and see what happens.
Best intentions. I always have the best intentions.
All right, so we've got some water. The water will be a factor. More pumpkins will be near the water, less far away. Soil and sun. Oh, someone said about, I missed it, salt in the soil from the salt from the road. Yes, in Montana, I think you've probably had your road salted recently.
All right, so we're going to start out with trying to make an approximation about how many pumpkins are in our entire field here. And so I tell my students, okay, if you've ever been out to any sort of a garden situation, you know, I might not want to like weed through all of the pumpkins to get to the other side of the field. I don't want to trip over things. I don't want to get tangled. So it might be just nice and simple to just sample all 10 of those places along the road. So the way that the activity works on the calculator is you can just click right on the squares, and those then will become part of your sample. If you accidentally click on a square, you can actually click off of it and it'll make it unselected for you. Deselected, I guess. So I have 100 squares, and I'm going to take a sample of 10. So if Tracy clicks the total there, we'll have a sum of 154 pumpkins in our patch. That sounds like a lot to go harvest because you have 100 squares, and that's just the sum for 10 of them. So if we multiply that by 10, you're going to have a grand total of 1,500 pumpkins in your patch. But you know, that sounds like an awful lot of work to go sample all these pumpkins. So maybe instead of going along the road, I wonder what would happen. A lot of you said that the water was going to play a big role in our pumpkin patch. So what happens if we maybe lazily went along the river, maybe fishing as we're going and counting all of our pumpkins that are along the river? Oh,
Wow.
along the river. Some of you are right. Water might make a difference. So we went from an average of 15.4 to an average of 28.4. So almost doubled going along the river, which someone has noticed the sample is probably not accurate because you're only using part of the patch. First one is a convenience sample.
Mhm.
And I don't, you might even say the second one might even be a convenience sample because I'd rather go fishing while I'm counting, you know, than going right along the road. So if you were going to teach us with your statistics students, what might be some better methods that might maybe account for the fact that maybe along the road and along the river, maybe your situations are different? What might we be able to do instead? Go ahead and put that in the chat.
Random 10. Stratify with columns as strata. Diagonal X. Sample along a diagonal.
All right, so Tracy, why don't you go ahead and you're already clicked on the road. Someone said to stratify by the columns. What if we stratified by the road because your mouse is already there? Do you think you
Okay.
could get this to make a random sample for you?
Oh, yes, I can, because I read the directions on 1.1. It says if I click along the road, it'll randomly select a block in that row. So I can get my 10 random samples using the rows as strata.
So along the rows, we now end up with an average of what, 26.9. So for those of you who are keeping track, our original along the road was 15.4. Along the river was 28.4, and now going by rows is 26.9. All right, so I
Better
wonder if
but not
somebody,
great. Someone says better but not great.
so I wonder if somebody did this, somebody else, like another student did this, what their answers would look like. Tracy, what do you think? If I had like, if I gave this to a different student
Well,
and
let's
they
have a
did another
different
sample.
student randomly. I hope they realize, and they'll find out if each student is doing their own, they're each going to get a different sample. So now I only have 229. I told you, I just throw it in and see what happens. Not doing so well.
So with my students, we actually do a little bit of data collection, and I have every student do what we've just done going across. Do you have to seed your calculator? The answer to that is usually I tell the kids to seed anyhow. I'm 99% sure that in the code that it's pulling a random seed anyhow. But just to make sure my kids always set their random seed on their calculators before we do any sort of a simulation. But I'm pretty sure in the code that this one is set for that.
Yeah, and I think
So
so, because I think this is different answers from when I've done it before.
it is, and I can tell you that
Mhm.
when we did it in class, I'm pretty sure that it's got a random seed in there.
Yeah.
So this is a really nice data collection activity with the kids because then you can have them plot those values on a nice dot plot. And you can come up with like a class mean for the rows. You can come up with a standard deviation for the rows. But then you could say, someone had mentioned, do the rows and the columns have something different with them? Is it better to sample by the rows and sample by the columns?
So now I'm clicking on the water area to get a random sample of the columns, and I get a total of 237. Why would it be, why might rows be a little bit better than the columns, thinking about the situation that we have? Someone want to put that in the chat? Because I'm leaning towards, I'm liking the row, especially just looking at this even, I'm liking doing the rows better than the columns.
So good observation. If you go just by columns, you could end up with all of them along the water.
Yeah. Or I was thinking I didn't get any along the water this time, get nothing along the water. Whereas if you do rows, you're at least going to guarantee, I should clear first, guarantee you're going to get something near the water, something a little bit further away, because we really the water's definitely got something to do with how pumpkins grow.
And the way it's coded, if you have the students do it both by columns and by rows, the variability one has a smaller variability than the other. And I'm pretty sure that you're right. If you sample, we made the water the higher influencer for numbers. Somebody did ask, can you just click on one and see what's in one cell?
Let's try it. Yes.
And that's actually how we end up with what's really in the field. At the end, we do a big reveal, or if the kids stumble upon it on their own, they'll click on all 100 squares and go, I already know the answer. Here's what's in there by the time they're at the end. But it does take a little bit of work to do that.
And we all have that student that will do that.
All right, what's another sampling method we might want to use here? What do you guys think? We've talked about strata. We could do systematic.
Systematic.
Okay. Oh, totally random sample. I wonder how I could do a totally random sample there.
Yeah, simple. How in the, oh, Becky, I think you're going to need to show us something really cool that if you were given this file, you might not even know it's there unless you read directions, which I'm a teacher. I don't usually read directions. I jump in and I play first. So there's
Oh, I
one
always
thing.
Oh, I even forgot too when the kids got there. I always tell the kids for statistics, my favorite button is the menu button because that's where all of my options are for statistics. Well, if you hit the menu button, you'll notice under select, there is a simple random sample. You can actually get it to do the columns and the rows stratification for you all 10 samples at once. But if you click on simple random sample, there is my nice simple random sample. Everyone had an equal opportunity, and there's my mean.
Nice.
And so again, I would have all of my students do this, and we would do on the board a nice little dot plot and have the kids plot their values. So we could kind of see what the typical or where it's centered for all of our samples. And I could kind of see what does the spread look like, because some of these, like I said, I know the rows and the columns, the spread is different. And so it's kind of a nice conversational point to have with your kids.
And there's one other one underneath the menu select sampling method. Do y'all notice it? Cluster. This is for that lazy person who wants to not really just find a spot and grab everything around, not wait very long. So you can do two kinds of clusters, come up with their totals. I'll tell you, one of the things that I really like about this, I've done something similar, but with a worksheet where all the numbers were there and they did the work on the side, and they had a lot of, I call it the grunt work to do, a lot of the calculations, the adding them all up and calculating the mean, which is not hard, but it takes away from the process of learning what different sampling methods. And so I like that that piece of this type of activity is kind of taken out of the hands of the students so we can focus on the sampling methods and have good discussions around that. Now, along with the TNS files, Becky has also created some worksheets that you will get them in Word version so that you can change them if you like. Do you want to show them that for this one, Becky?
Yeah, because we were going to talk about that second page. Yep.
Yeah. I jumped to the second page on this one. And so what are we doing on these?
So this is what we were talking about. So this one says to have the students do a simple random sample. So the picture is there. I have the kids actually color in on the image off to the left-hand side, the 10 that they sampled, because when we get to our class dot plot up on the board and we're copying it on the paper, it's kind of nice to say, okay, those of you who had a higher average, can you tell me what your dot plot or what your field looked like for your sample? Those of you in a lower mean, can you tell what they look like? And so the kids can kind of come up with why those numbers might have an outlier one way or the other. But then having them write it on the board. This is an early on activity I do in the fall. And one thing I find with my students is that they really struggle trying to get data collection and figure out in their head what that scale should be. So as they're looking on the board, trying to figure out, okay, what do I increment my dot plots by? And so I like to kind of leave this worksheet open-ended, and I have them wait until everybody's data is on the board. And then we kind of develop as a class, what should my scale look like? What are the maxes? What are the mins? And what are we incrementing by? Just to kind of reinforce those skills from earlier in the year.
Yeah, I thought that was interesting because at first I noticed there's no scaling, and I course, asked her, why isn't there any scaling on this? And she reminds us of they have trouble with some of that stuff that we think, oh, this is going to be the easy part, put those plots on. But some students really have trouble thinking about the best way to plot their raw data then. And it does it for different samples. Ask them to do stratified, each row, and then there's cluster. So they can see all of those different class data plots then. And then I like the follow-up questions. What methods have smaller variabilities? Which methods have the largest variabilities? And reminding them what our ultimate goal is. And then, of course, how many pumpkins do you think are in the entire field? And then justify. They have trouble justifying, at least my students do. Just because.
All right, so that's our first activity to kind of set the stage, talking about how to get samples. This one, everybody has the same field. And so if everybody clicked in the top left-hand square and made a reveal, they'd all have the same value, so that way we're talking about the same field when we're collecting our data, and they can see how those different data collections would result in different sample means. The second file that we're going to switch to for sampling distributions, also, I know has a random seed, I'm pretty sure, in the code here, because it doesn't ask you for a random seed for it. And so this one actually is going to be different for every student. So as they're comparing their answers when they're not, or when they're taking a random sample on purpose, everyone is going to be different. So for this sampling distribution activity, we're going to start with a nice little normal distribution. It tells the students what the population mean is and the standard deviation for their sample. And to begin with, we're just going to take a nice little sample of 5 data points out of our uniform distribution. And you'll notice it shows you those 5 values. And then it plots on the bottom the mean of your one sample. And so the very first question I asked my students, because this is again early on, is can they describe the top graph? And so they'll talk about the shape, the center, and the spread. And then after we take the very first sample, I asked the kids, okay, so you've got one mean below. If I were to let you take multiple samples over and over and over again, what do you think the shape, center, and spread would be down below if I let you repeatedly take samples of size 5?
And I really like how you're kind of asking them to predict without doing it. What do you think's going to happen?
And on the worksheet, you'll notice that this one we do very deliberate, very slow, to ask them every single time they take a sample to make some predictions and fine tune those predictions. So the first question is going to ask them to define the population. The second one, they're going to only take one sample, so they get in their head that they're taking only 5 pieces of 5 data points and averaging them. And then they're going to take 19 more, and then they're going to make some predictions as to what do they think is going to happen with the shape.
Can I take my 19 more?
You can take your 19 more. And what's nice is notice each time she takes a sample on the bottom, the new point that's added is in yellow. The old points are in blue, so that they can kind of see how that most recent sample has been added to their distribution of sample means down below.
And in case you're worried, because I was at first, it's keeping track of how many times I've clicked at the bottom. So I know when I've hit 19 more.
So now in the chat, what are you noticing about the distribution of the sample means? If you were asked to describe that distribution, what would you say? Getting some normals. Less variable than the population.
I like the close to normal.
Oh, some of you are thinking it's unimodal, which it looks unimodal. Okay. What other vocab words can we use?
Approximately normal, yes. Symmetric, nice.
Okay.
Roughly symmetric.
All right. So sample mean is getting closer to 40. And actually, that's one of the questions on the worksheet for them to look at, is to kind of compare the sample mean to the population mean. So that's a good observation.
And I like notice in that part after this, they're also comparing with their neighbors' sample means. Because remember, everybody is getting their own distribution of sample means right now. They're not the same because they're each getting randomly generated their own samples. So I think that variability is important to constantly point out to students.
All right, so the next one has them jump to a total of 30. And you might be thinking to yourself, poor Tracy is going to have to click this 280 more times. But
Don't
that's
worry.
actually, you got your exercise finger ready to go there.
Boom. I'm doing 30 at a time now.
And
I
then
was worried.
and so then notice it jumps to taking 50 at a time for the students, just so that they're not clicking over and over and over again. And Tracy's using the button, but you can actually just hit the enter button on the calculator and it will take another sample for you. All right, so we have 350, we have 400. What do y'all think? He said approximately normal after we'd only done 20. After 400, are you guys still gonna go with the approximately normal?
Yes. Yeah. Much closer. And this is for the Nspire. There is not anything for the 84 like this, but somebody did mention in the chat, there are applets also on the internet that do something very similar. I have Nspires. I'm fortunate in my classroom that each of my students have Nspires. And so getting their hands on it, unless everyone's got a computer, it's really nice for them to actually do this individually instead of me just showing it up on the screen.
All right, so I want you to take a look at the standard deviation at the top for your sampling distribution and the standard deviation for your distribution of sample means. And we have a good conversation as a class. Notice the means are approximately equivalent, but your standard deviations are not. And so at this point, I have my students make a prediction. How do you think the distribution or your standard deviation for your population compares to the one below? Is there some math that we can do to calculate that out? And typically at this point, my students tell me it's about roughly half. They'll tell me that my distribution of my sample means look like it's roughly half that of the population. And that's a very typical answer. So then it would be nice to say, okay, so if it's roughly half, what happens if you change your sample size? And somebody already said menu earlier. So if you hit the menu, there is a way to change your sample size. And so let's go ahead and change it to 30. Noticing our standard deviation had been 10.5. So I'm going to write that down that it was 10.5 from before. And then Tracy can now just repeat the process. She can go ahead and sample. And it works just like before. It takes it one at a time till you hit 20. And then they go by 50s. And now they're like, oh, yeah, no, it's not half.
Not anymore. So
And so
what did we change? It's not a half anymore. So what would have affected it?
Sample size. So
Sample
let's make a
size.
prediction. If Tracy changes the sample size to, I think was 100 an option, Tracy?
Oh, no, 40. What was the,
What was the next
don't
one?
see that. 50.
If Tracy changes it to 50, let's make a prediction. What do you think will happen to the standard deviation for our distribution of sample means? Do you think it's going to be the same? So it's going to be 4.4-ish. Is it going to get smaller? Is it going to increase?
Well, what was
All
it
right.
again when I did a sample size of 5? You wrote it down and I didn't.
10.5.
Okay, thank you. And then I went to 4.4-ish. So I'm going to say, I
Yep.
don't know, 2, just because.
All right, so let's check Tracy's hypothesis out and see if she gets to 2.
Come on, come on. No, too much. I went too far.
She's about 3.2. So on the worksheet, the students do the same thing that Tracy just did. They will keep it a normal distribution, but they will change the sample size, and they'll notice as the sample size increases, their standard deviation decreases. And then it's really kind of funny because when Tracy scrolls down here, you're going to notice that the formula is on the page, and I'm asking the kids usually, so how do you think we're going to calculate this? And they don't jump ahead. I don't know why they don't jump ahead to get to the punchline. But then at the bottom, it does show them theoretically how to get the standard deviation, and then they will compare that to what they've got and see if it kind of looks like they're approximately the same values.
And so if you have a class, you know that it has that student, here's where having the Word version of this document will be handy. Maybe cover that up. I don't always have that student, but sometimes I do.
All right, so then the question is, does this phenomenon that you can take the standard deviation and divide by the sample size, does that hold for other distributions? So what type of a distribution would you guys like to see for, oh, actually, Tracy, let's not even go to the menu. Tracy,
Oh,
why don't you
you're
just
gonna show
draw
them the
like an
fun
arts?
first?
Yeah, let's
Okay.
do the fun first. Why don't you just draw like an art student?
Okay. I was practicing to come up, ooh, don't go too fast, to come up with something
So
interesting.
if she just clicks and holds the mouse, you're allowed to go ahead and change the shape of your sampling distribution, or sorry, your population distribution. And the kids really kind of get into being creative and trying to come up with different patterns and see what they can kind of come
Yeah.
up with for
Okay,
distribution.
I'm happy with that one.
All right, and so then we just said that the formula was the standard deviation over the square root of n. So Tracy, let's go to a quick scratch pad because we know the standard deviation for yours is a 21.78. And we're going to divide by the square root of n. What sample size do you want to use?
Let's do the 30.
Okay.
So
So 3.98.
8, yep.
All right, so then we can go put it into practice and do the exact same thing as before. So you can take a sample of size 30. We're looking for 3.98.
Pretty darn close.
All right, so you could have your kids do all sorts of different shapes and have them check this out. What is one more thing you might want to discuss with your kids using an app like this? What's one other important conversation that might need to occur here? Any ideas where we might have a little bit of a misconception going on? A central limit theorem. Ooh, skewed distributions with a small sample distribution size. Okay. So Tracy, do you want to go ahead and investigate that one? Let's make the original shape skewed. And let's keep the sample size at 5. So let's go back and make it small. And let's go ahead and kind of take a look to see. So this is one when you're going to try to talk to kids about sample size and trying to decide if it's skewed or not skewed, to really point out to them to use up top the scale to kind of approximate where is the center of that distribution. And then kind of use that as a line of symmetry and ask them, does the spread on the right-hand side look approximately the same as the spread on the left-hand side? That's one thing that my students kind of gloss over when we do this activity. So I really have to point out with them when they're drawing their sketches on their notes, which ones really are approximately normal and which ones are definitely skewed. And if you wanted to make it even more skewed than what I've got there, because you saw that Tracy could draw, she could fill that in even more in the upper right-hand corner if she wanted to give it. The population wasn't badly skewed. We could really make that a badly skewed population, and you can illustrate with your kids how that sample size really needs to be over 30.
And so Becky has the worksheet laid out really nicely to help with some of this guided exploration to see. Someone had an interesting question. Will it hold for other statistics?
I think there's a page for that.
Oh, awesome. I love it when we plant people in the audience.
Right. So
Thank you,
page
Jordan.
2 is exactly like page 1, or I guess this is page, what, 1.4 is the same as 1.2, only now it's going to measure the medians and not the means. So you can explore with your students, that does this hold? Can you still take and do the standard deviation over the square root of n? And they can kind of look at, does that 30 number still kind of appear, just eyeballing it, if it looks like it's approximately normal.
And I like doing other statistics too with them for that reason. So I don't think we always have to be looking at mean, even though our focus in AP statistics is typically proportions and means. There are other statistics that statisticians do use and investigate. So, okay, I think we're ready to move on to stimulating simulations number 3.
All right, so now that we've done sampling distributions for one population, I wonder what it looks like if you have two populations and you take a sample from one and a sample from the other and maybe add those together. So you're going to notice the layout of this one looks really similar. So you'll notice we have that nice, I don't know, magenta color on the left-hand side. That's a nice normal distribution, or nice uniform distribution. But we're going to take one and only one sample from that population, and we're going to partner it with a sample from the blue population on the right. So if you'll notice now in the middle box, it says I got a 27 from the purple population and I got a 40 from the blue population. So now when I combine those, I get a nice sum of 67. That's kind of maybe a nice point to talk about right now. How come the standard deviation and the variance down below is 0?
You only have one value. You're not varying at all.
So there's no variation. Okay. All right, go ahead and take another sample. Okay, let's stop at 2. That's interesting. So using the populations from above, notice the purple population has a mean of 20. They both have a standard deviation of 14.7. And they both have, oh, sorry, that's a variance. And they both have a standard deviation of 11.84. After 2 samples where I've added them together, my distribution of sample sums has a mean of 68, a variance of 2, and a standard deviation of 1.41. What do I think it's going to look like as I take more samples? Sample sizes right here, and you called me out on it. Yep, sample size right now is only 1. We're going to get to over 30, but right now we're going to kind of set up the premise for them to realize that we're going to do kind of a matched pairs here. So you're going to have 1 from the population's purple and 1 from the blue, so I can sum those together. So to begin with, we're going to start with just the 1 sample and with the visuals on the side, because when you start taking 30 samples, little calculators don't have enough real estate on the screen to show students that you have 30 samples, that you're getting 1 purple, 1 blue, combining them together, and then doing my 30 samples there. All right, so if you'll go ahead and a sample there, and it's going by one at a time, so the students can kind of make the connection between what are we sampling and how are we getting the distribution.
I can't remember, when does this one jump?
I was just sitting here going, I don't know if this one jumps. You're gonna have to go change it to jump. I might not have made it jump on its own. If you hit menu, will tell you change the sample size. I'm pretty sure it does.
Yeah.
Oh, just a sample size, so
Yeah.
don't do that. Yeah, don't do
Okay.
that. Well, okay, there we go. We just hit the enter button a whole lot.
Yeah.
So even though at 142, students can kind of start making some comparisons. If you look at the means for the populations and the variances for the populations and the standard deviations for the populations, say that 10 times fast, how do they compare to my distribution of my sample sums down below? What are some observations?
Mean is the sum of the means. They are both double.
Is everything double?
Okay.
Something else with standard deviation. Variance is close to the sum.
But that's not quite double. Just mean and variance are doubled.
So then this is where you start having the students try to make some predictions. How can they go from the variance to the standard deviation? And if you covered that earlier in the year, they might be like, oh yeah, that's how those two are related. So now that Tracy has done this one sample at a time, so your students understand that you're doing one from the pink population and one from the blue population and summing them. But you've done that sampling distribution from before to realize your sample size probably should be more than 30. We can change the sample size to 5 if you want to reinforce with the kids how this matching is going to work. Because with 5, you still have a little bit of real estate on there. Oh, you might need to go clear that, Tracy.
Oh, sorry.
And so now notice 5 barely fits on the real estate, but they can see I'm taking 5 values from the pink population and 5 from the blue, and I'm pairing them together, finding the sums, and then taking the mean of that sample.
This is going a little faster. I think that visual of them seeing that connection of what they're actually doing is so important, because they forget that there's multiple ways to get, this one doesn't have a duplicate of 36. There's different ways. I like stopping at a screen where they're seeing 2 of the same sums. There we go. 16 and 22 and 8 and 30. That's something I know my students, they know it, but they don't really understand it in the situation.
And then this file is just like the other distribution file. So if Tracy wants to channel her inner artistic, she can actually change the population distribution to any shape her heart desires.
Get a really skewed one this time. Oh, go on, go away, go away. Okay, I'm not being creative. There we go.
This actually does work on the iPad app. If you have the Nspire iPad app on there, you can download it, and it works really well on the iPad.
Very nice, very nice. Is that all that's in this Nspire document?
Oh no. What would be
Oh.
nice, y'all? Any ideas what would be nice to be on the next page? What might we want to explore?
In a combining variables, we looked at the sum.
The standard deviation, subtract them.
Them.
Subtraction would be nice. And this
Yes.
one, I think is really helpful with kids because my kids always want to just subtract those standard deviations from one another.
Yes. So it's set up exactly the same way. Let's do 50. We didn't do 50 on the other one. Can't see them all, but nice.
Okay, so we started with how to collect data. We talked with different sampling or different ways to take samples. We've gone to sampling distributions. Now we're going to jump into hypothesis testing with you and talk a little type 1, type 2 error. So this one does not have the random seed in the code. So for those of you who have been waiting for the random seed to pop up, I did this activity today with my students, and if they all type in the same random seed, you all know what they're going to get, the same results. So I told them to put their birthdays, real birthdays, but they can put anything they want in here to randomly seed the calculator so they don't match their neighbors. For this one, you don't want them to match their neighbors at all. So Tracy, you're actually going to want to put random seed in front of that.
Oh yeah, duh. I'm excited about trying to remember my dog's birthday because I don't want to put in my birthday.
So they just have to put a random seed and hit enter, and then that will go ahead and random seed their calculator so that theirs is different from their neighbors. So I don't know about you, Tracy, but probably type 1, type 2 errors and powers are not necessarily some of my favorite topics to teach just because I think they're really hard for kids to grasp. What do you think?
No. Power, oh, the first year I was so determined to teach power. I spent 2 days each day going back and saying, well, I'm going to do better than I did yesterday. I actually think it went into 3 days before I finally said, you know, I understand it, but not enough to really get you to understand it. So let's just call it a day. This first year of teaching AP statistics, it did not happen in my room at all. And it still was a couple years later before I started doing better at teaching it. So, Becky, I love your story about what inspired you to create this Nspire file.
I told Tracy, I said, I like to put power off to the end because I think it's really hard for them to grasp. And so one year I put it off to the very, very end, like 2 days before the AP test, we taught it and reviewed, and the kids came back in and they were so excited because it was somewhere on the test. I don't know where, somewhere on the test. They were so excited they could do power. And all I could think of was, I don't know that you guys grasp power. There's got to be a better way for me to teach this for you. And so I sat down and I'm like, I've got to get what's in my head onto some sort of app for you guys to play with. And so that's actually where this came from, is how to get them to play, to understand really how are we getting those probabilities from type 1, type 2 errors. So now that you have a nice random seed, let's go ahead and go to the first page. So there's a story that goes with this that says you have an infinite candy jar that has a population proportion of 6, or there you go. So you have an infinite jar of candies. 60% of your candies are green, 40% of them are some other colors. And you've been hired to do some quality control to see, is the true population proportion of green, that's my school color, really 60%, or are they not 60%? So it's just a simple null hypothesis of P is 0.6 or P is not 0.6. So what are you going to do? You're going to go out and you're going to take a sample. So I told him I can't send them all to a candy store and have them take a random sample. We could go get all sorts of candy to go do that. But on our sampling distribution app, I can send them all out to really quickly do a sample. So here's what's going to happen. She's going to hit the sample button. She's going to go out and sample 30 candies and collect how many of them are green. And we're going to plot that proportion. And so out of her sample, only 0.704 of them happen to be green. And so where they've landed on our normal distribution is in a region where I would fail to reject, because it's only, looks like maybe roughly more than 1 standard deviation away, which is exactly where those are marked out. You can have your kids actually calculate the standard deviation for this scenario where the sample size is 30 and verify that those are 1 standard deviation and 2 standard deviations away from the mean. But remember, you have your kids randomly see their calculator. Not everybody's is the same. So if Tracy took another sample, the kid sitting next to her might end up with the reject. And if she does another one to represent the kid sitting behind her, they're going to fail to reject. So what I have my students do is get into small groups of 6 to 8 and have each of them take 1 sample and look at, does their sample cause them to reject or fail to reject? And then they kind of look around the room in their groups and they talk about, did everybody get similar results? Why or why not? So then I'm going to ask, how could we maybe investigate this further? So how could we come up with, should we really reject or fail to reject? Like, is our sample really representative of the whole population? And is it telling us that we really should fail to reject or not? So if we go to the next page, we're going to build off of that last applet with our sampling distribution. And this one's going to let the kids repeatedly take their samples. So instead of erasing each time they take a sample, now Tracy's up to 5 and she's got roughly a 20% rejection rate. So if she pauses here, what do you guys think? Just looking at the 10 samples she's taken, do you think the true population proportion of green is really 0.6? Or looking at her 10 samples, do you think it's not 0.6?
Some knots. Looks to be larger than 0.6, higher, not.
All right, let's go ahead and take some samples and check that out. Notice the 50 did pop up here.
Yay.
Does look higher, but it was only 10 samples.
I'm getting more evidence now.
260 samples. And so as they start to take their more and more samples, they're going to start to develop that sampling distribution. And then they'll notice what you guys have noticed, that the population proportion is not really 0.6. It is actually higher, but there's so much overlap between this 0.6 and what appears to be maybe, I don't know, 0.7-ish, 0.68-ish, that there were a lot of data points that were actually going to cause me to fail to reject just because of the overlap in those sampling distributions. Okay, so from here, it might be nice if Tracy could, I don't know, change the sample size or change her actual population. So if you go to the next page, or it could be 2 pages over.
2. 3 pages.
3. Now the students are actually allowed to change both the null hypothesis and the actual population proportion, and they can change the sample size. So at this point, if you want to talk to your students about the probability of a type 1 error, you could actually set both of those guys to equivalence. So have the null hypothesis and the population proportion be set to 0.6. So if the population really is 0.6 and the null hypothesis is 0.6, we know the population is 0.6, that we probably shouldn't reject. But what we know about sampling distributions is 5% of the time, if that's where my alpha level is, I'm going to reject. So in the worksheet with the kids, you're going to have them do a bunch of setting the population proportion the same as the null hypothesis and letting them change the sample size to come up with, does the sample size let you change whether or not the probability you reject or fail to reject when the population proportion is really centered. at your null hypothesis. And then you can do the same thing with a type 2 error. You can make it so your null hypothesis and your alternative hypothesis, or your null hypothesis and your population parameters are not the same. And you can talk about the probability of making a type 2 error. So you fail to reject, but we can tell that it's really there. And I'm looking at the time here, Tracy. We're like,
yeah, this is a beautiful visual of this. And like I said, this to me is still to this day, like one of the hardest things to teach students because it puts so much of it all together. And I'm with you. I like wait until one of the very last things that I do is teach power because they've got to get really comfortable with sampling distributions and tests before this is really going to make sense. And so I just want to point out the worksheet that you have that goes with this is describing exactly how she has the students working through this. I know we went through that really fast.
And so then it's going to tell the kids exactly what to set the populations and the proportions to go to. The 2 pages we haven't shown you yet, but again, you guys get the files, will actually let you change the alpha level as well. And so you can explore as you increase or decrease the alpha level, how does that change the probability for a type 1 or a type 2 error? And then the very last page is kind of that traditional picture that I've seen in a lot of textbooks where you get to compare the distribution for your hypotheses versus against something and look at your probabilities. So again, the worksheets will be there and the TNS files will be there for you.
And hats off to Becky. This is all Becky's stuff. I'm just going to use it in my classroom. Like we all are now, probably.
I'm just glad it goes to some good use.
Oh, I know you worked really hard on this. And now I got to say, I already tweaked one of her files. So do not, that's just kind of how I am. That's how we all are. So that's why she's been so nice to give us the Word files. Thank you so much, Becky, for that.
You're welcome.
Becky, so quick question. I know a lot of people, especially at the beginning, were asking about the 84. So what did you use to create these files on the Nspire? Which coding language?
So it's actually coded in Lua. Lua is embedded in the Nspire language. It's not on the 84, and so you can't jump drive it. You can't bring it over to an 84.
Thanks. I know a lot of people are probably still using the 84 in their classrooms. And I just want to mention that, you can get a free trial version of the Nspire if you're interested on our website with all the files that Becky spent time creating. You'll get all of those tonight. And although, like Tracy mentioned earlier, it's really great whenever students can actually have this file in their hands on a handheld, playing, noticing, wondering. If you don't have that opportunity, I still think that students would benefit from this being in front of them, large and in charge, even if you just use the teacher software and you're demonstrating some of this.
But definitely when we were locked down last year, my kids didn't have anything at home. That's exactly how I taught. I just presented it on my screen. The kids didn't even have the files.
Right. Well, we're getting close to the end here. So if you have any questions for Becky or Tracy, please try to get those asked. I know they'll do their best in the short amount of time we have to get those answered. To receive a certificate of attendance, go ahead and click the links in the chat window. One is a link for the certificate for tonight, and the other is a link for the documents. If you're watching this on demand, go ahead and copy your certificate link into your favorite browser to receive your certificate. And if either of these links are not working for any reason tonight, just hang tight. You'll automatically get a follow-up email with links to the certificate, the recording, and the documents within a few days.
Good question. What am I working on next? I have not decided that yet. Anybody have any good ideas?
So you could actually, if you're interested, you can leave those ideas in the post-webinar survey. And I can get those over to Becky and Tracy and the TI team, and maybe one of your ideas will come to fruition. There we go. So when you leave the webinar, a brief survey will automatically appear in your browser. Your feedback truly guides us as we plan future online events, so we hope you'll share your thoughts in the post-webinar survey. So huge thanks to Becky and Tracy for everything you created and shared tonight. It was definitely exciting to see the visuals that can be created in statistics. So thanks so much for all of that tonight.
Thanks for having us. Thanks for coming, everyone.
Yes, it was awesome.
I agree. Thanks so much for joining us, and we hope to see you back online next week. Have a great night.
Good night.
Night.